The following lecture is one of a series that covers the HNC Electrical Engineering Unit, FY 9E, DC and AC Principles. This lecture presents a number of techniques to analyze resistive circuits that have a combination of series and parallel elements. This lecture makes extensive use of Ohm's law and introduces Kirchhoff's voltage and current laws. The subject elements to be covered in this lecture are as listed on this slide. A summary of all the information covered, the worked examples, and a set of self-assessment questions are contained in the accompanying workbook. Resistance is the term given to the ratio of the applied voltage to the resultant current flow in a body. A body is said to have a low resistance if a relatively small voltage results in a large current, and a high resistance if a large voltage results in a relatively small current. The symbol associated with the resistance is the letter uppercase R, and its unit is the ohm, abbreviated to the Greek letter omega. Resistance is represented in a circuit diagram by the symbol shown. There is a relationship between resistance, voltage, and current. The highlighted box shows resistance is equal to the voltage divided by the current. Provided the voltage is in volts and the current is in amperes, then the resistance calculated will be in ohms. This relationship is known as Ohm's law and is the basis of all the electrical network theorems. It does not matter what part of an electrical network is examined, Ohm's law always holds true. Ohm's law enables that for any given situation where two of the three electrical factors are known, the third to be derived. Using the triangular representation of the law, if the voltage and the current are known, the resistance may be determined. If the current and the resistance are known, then the voltage across the device may be determined. Finally, if the voltage across the device is known and its resistance, then the current flowing through the device may be calculated. A series circuit is one in which all the components are connected nose to tail. So, in the circuit fragment shown, the three components R1, R2, and R3 are all connected in series. The potential arrow indicates the voltage V across the circuit and hence determines the direction of current flow. In a series circuit, the same current will flow through each component. By Ohm's law, that current flow will give rise to a potential difference across each resistor, V1, V2, and V3. By inspection, the terminal voltage V must equal the sum of V1, V2, and V3. Applying Ohm's law and substituting for V1, V2, and V3, V equals I times R1 plus I times R2 plus I times R3. Taking out I as the common factor, V equals I times R1 plus R2 plus R3. Dividing through by I, V divided by I equals R1 plus R2 plus R3. Since V is the total circuit voltage and I is the total circuit current, then by definition this must equal the total circuit resistance Rs. An equivalent of the series circuit may therefore be drawn where resistors R1, R2 and R3 are replaced by a single resistor Rs. The highlighted box shows that where there are a number of resistors connected in series, they may be replaced by an equivalent resistor Rs, where Rs is equal to the sum of the individual resistors. The following example is in the accompanying workbook, Resistive Circuits, Series Circuits. Here, we are required to determine the total resistance of the circuit current, and finally, the voltage across each resistor. To find the total circuit resistance. The total resistance of a series-connected circuit is the sum of all the individual resistors. Substituting the values, Rs equals 10 plus 20 plus 30, which equals 60 ohms. To find the total circuit current. By Ohm's law, we know the total circuit current I equals the total circuit voltage V divided by the total circuit resistance Rs. Substituting the values, I equals 15 divided by 60, which equals 0.25 amperes. To find the voltage across each of the resistors. Since the resistors are all in series, they all have the same current flowing through them, so we can use Ohm's law to find the voltage in each case. Substituting the values, V1 equals 0.25 times 10, which equals 2.5 volts. V2 equals 0.25 times 20, which equals 5 volts. And V3 equals 0.25 times 30, which equals 7.5 volts. We can do a check on the answer at this point, since we know that the sum of V1, V2 and V3 should equal the total voltage V across the circuit. Substituting the values, V equals 2.5 plus 5 plus 7.5, which equals 15 volts, the circuit voltage. This video clip is a simulation of the example and shows how the circuit current and each resistor voltage would be measured in practice. One DMM is set to read DC current and is connected in series with the resistors. Then each of the resistors has a DMM connected across it, which is set to read DC voltage. When the switch is closed, the DMMs show the same values as those calculated within experimental limits. Series circuits are frequently used in electronic systems as a means of providing reference voltage levels, termed voltage divider circuits. Consider the series circuit shown. By Ohm's law, I equals V divided by Rs. The voltage across R1, V1, equals R1 times I. Substituting for I, V1 equals R1 times V divided by Rs, which may be rewritten as V1 equals V times R1 divided by Rs. Similarly, V2 equals V times R2 divided by Rs. And V3 equals V times R3 divided by Rs. The highlighted boxes show that the voltage drop across any resistor in a series circuit is equal to the ratio of that resistor to the total circuit resistance multiplied by the source voltage. The following example is in the accompanying workbook, Resistive Circuits, Voltage Division. Here, we are required to determine the voltage across each resistor using voltage division. The formula to calculate V1 is the circuit voltage V times R1 divided by the total series resistance Rs. We know the value of V and R1, but we need to first calculate the value of Rs. So, Rs equals R1 plus R2 plus R3. Substituting the values, Rs equals 10 plus 20 plus 30, which equals 60 ohms. Now we can continue to calculate each resistor voltage using voltage division. Substituting the values in the first equation, V1 equals 15 times 10 divided by 60, which equals 2.5 volts. V2 equals V times R2 divided by Rs. Substituting the values, V2 equals 15 times 20 divided by 60, which equals 5 volts. And V3 equals V times R3 divided by Rs. Substituting the values, V3 equals 15 times 30 divided by 60, which equals 7.5 volts. A parallel circuit is one in which the noses of all the components are connected together and all the tails are connected together. So in the circuit fragment shown, the three components R1, R2, and R3 are connected in parallel. The potential arrow indicates the voltage across the circuit and hence determines the direction of current flow. It should be noted that in a parallel circuit, the voltage across each component will be the same. As the current flowing into the circuit must be the same as the current flowing out of the circuit, the total circuit current I must equal the sum of the branch currents I1, I2, and I3. Applying Ohm's law and substituting for I1, I2, and I3, I equals V divided by R1 plus V divided by R2 plus V divided by R3. Taking out V as a common factor, I equals V times 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Dividing through by V, I divided by V equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Since I is the total circuit current and V is the total circuit voltage, then by definition this must equal not the total circuit resistance Rp, but 1 over Rp, termed the reciprocal of Rp. The actual value of Rp may finally be determined by simply taking the reciprocal of this result. An equivalent of the parallel circuit may therefore be drawn where resistors R1, R2, and R3 are replaced by a single resistor, Rp. The highlighted formula shows that where there are a number of resistors connected in parallel, they may be replaced by an equivalent resistor, Rp, where the reciprocal value of Rp is equal to the sum of the reciprocal values of the individual resistors. The following example is in the accompanying workbook, Resistive Circuits, Parallel Circuits. Here we are required to determine the total resistance of the circuit, the voltage across the circuit, and the current in each branch. To find the total circuit resistance. The reciprocal of the total resistance of a parallel connected circuit is the sum of the reciprocals of all the individual resistors. Substituting the values, 1 over Rp equals 1 over 10 plus 1 over 20 plus 1 over 30, which equals 0.183. That is the reciprocal of Rp. So Rp equals 1 divided by 0.183, which equals 5.45 ohms. To find the total circuit voltage V. By Ohm's law, we know the total circuit voltage V is equal to the total circuit current I times the total circuit resistance Rp. Substituting the values, V equals 2.75 times 5.45, which equals 15 volts. To find the current in each branch. Since the resistors are all in parallel, they all have the same voltage across them, so we can use Ohm's law to find the current in each case. So I1 equals V divided by R1. Substituting the values, I1 equals 15 divided by 10. Which equals 1.5 amperes. I2 equals V divided by R2. Substituting the values, I2 equals 15 divided by 20, which equals 0.75 amperes. And I3 equals V divided by R3. Substituting the values, I3 equals 15 divided by 30, which equals 0.5 amperes. We can do a check on the answer at this point, since we know the sum of I1, I2, and I3 should equal the total circuit current I. Substituting the values, I equals 1.5 plus 0.75 plus 0.5, which equals 2.75 amperes. This video clip is a simulation of the example and shows how the circuit and branch currents would be measured in practice. The DMM is connected to the main supply line, and one DMM is connected in series with each branch resistor. The DMMs are then set to read DC amps. When the switch is closed, the DMM values are the same as those calculated within experimental limits. Parallel circuits may also be considered as a means of dividing a current into a number of different parts. These are called current divider circuits. Consider the parallel circuit shown. By Ohm's law, V equals I times Rp. The current through R1, I1, equals V divided by R1. Substituting for V, I1 equals I times Rp divided by R1. This can be rewritten as I1 equals I times Rp divided by R1. Similarly, I2 equals I times Rp divided by R2. And I3 equals I times Rp divided by R3. The highlighted boxes show that the current flowing through any branch in a parallel circuit is equal to the ratio of the total circuit resistance to the branch resistor multiplied by the total circuit current. The following example is in the accompanying workbook, Resistive Circuits, Current Division. Here we are required to determine the current flowing through each branch of the circuit using current division. The formula to calculate the branch current I1 is the total circuit current I times the total parallel resistance Rp divided by the branch resistance R1. We know the value of I and R1, but we need to calculate the value of Rp. So, 1 over Rp equals 1 over R1 plus 1 over R2 plus 1 over R3. Substituting the values, 1 over Rp equals 1 over 10 plus 1 over 20 plus 1 over 30, which equals 0.183, the reciprocal of Rp, not Rp. So Rp equals 1 divided by 0.183. Therefore, Rp equals 5.45 ohms. Now we can continue to calculate each branch current using current division. So, I1 equals I times Rp divided by R1. Substituting the values, I1 equals 2.75 times 5.45 divided by 10, which equals 1.5 amperes. I2 equals I times Rp divided by R2. Substituting the values, I2 equals 2.75 times 5.45 divided by 20, which equals 0.75 amperes. And I3 equals I times Rp divided by R3. Substituting the values, I3 equals 2.75 times 5.45 divided by 30, which equals 0.5 amperes. Complex resistive networks will normally have resistors in both series and parallel. Whilst it may not always be necessary, sometimes the only way to fully analyze the circuit is to reduce it to a single element. There are three key reduction steps. Firstly, deal with the simple series branches. In this case, series branches RS1 and RS2. This reduces the circuit as shown in step 1. Then deal with the simple parallel branches. There is only one set of parallel branches, Rp. This reduces the circuit as shown in step 2. Finally, keep repeating steps 1 and 2 until only one element is left. In this case, we only have a set of series elements to consider, which equate to Rt, finally reducing the circuit to a single element. The following example is in the accompanying workbook, Resistive Circuits, Circuit Reduction Techniques. Here we are required to determine the total circuit resistance, the total circuit current, the current through each branch, and finally the voltage across each element. To find the total circuit resistance, Rt, using the key reduction steps. Step 1. Deal with the simple series branches, of which there are two, RS1 and RS2. So, RS1 equals 4 plus 8, which equals 12 ohms, and RS2 equals 6 plus 10, which equals 16 ohms. Step 2. Deal with the simple parallel branches, of which there is only one, Rp. So, 1 over Rp equals 1 over 12 plus 1 over 16, which equals 0.146. Therefore, Rp equals 1 divided by 0.146, which equals 6.85 ohms. Step 3. Repeat steps 1 and 2 until only one element is left, Rt. So, Rt equals the sum of the series elements, which equal 2 plus 6.85 plus 12. Therefore, Rt equals 20.9 ohms. To find the total circuit current I, applying Ohm's law to the equivalent circuit from step 3, so I equals V divided by R. Substituting the values, I equals 15 divided by 20.9, which equals 0.718 amperes. To find the branch currents using current division. The equivalent circuit obtained in step 1 is the best starting point to determine the branch currents as it has single elements R1 and R2 in the parallel paths. From the equivalent circuit obtained in step 2, we can see the total resistance Rp of the parallel paths. So, I1 equals I times Rp divided by R1. Substituting the values, I1 equals 0.718 times 6.85 divided by 12, which equals 0.41 amperes. I2 equals I times Rp divided by R2. Substituting the values, I2 equals 0.718 times 6.85 divided by 16, which equals 0.307 amperes. Finally, to find the voltage across each resistor. As we know the value of all the currents flowing in the circuit and the value of all the resistors, we can calculate the voltage across each resistor using Ohm's law. V1, the voltage across the 2 ohm resistor, equals 0.718 times 2, which equals 1.44 volts. V2, the voltage across the 4 ohm resistor, equals 0.41 times 4, which equals 1.64 volts. V3, the voltage across the 6 ohm resistor, equals 0.307 times 6, which equals 1.84 volts. V4, the voltage across the 8 ohm resistor, equals 0.41 times 8, which equals 3.28 volts. V5, the voltage across the 10 ohm resistor, equals 0.307 times 10, which equals 3.07 volts. And finally, V6, the voltage across the 12 ohm resistor, equals 0.718 times 12, which equals 8.62 volts. Kirchhoff's current law, KCL, states that the sum of the currents entering a junction is equal to the sum of the currents leaving a junction. Or more simply stated, currents in equals currents out. Looking at the junctions shown, I1 and I2 are the currents going into the junction, and I3, I4, and I5 are the currents coming out. So, by KCL, currents in equal currents out. Therefore, I1 plus I2 equals I3 plus I4 plus I5. The following example is in the accompanying workbook, Resistive Circuits, Kirchhoff's Current Law. Here we have been shown a junction with a number of currents entering and leaving the junction. And we have been asked to calculate the value of I4. By KCL, currents in equal currents out. So I1 plus I2 equals I3 plus I4 plus I5. Substituting values, 3 plus 10 equals 2 plus I4 plus 6. Simplifying, 13 equals 8 plus I4. Rearranging, 13 minus 8 equals I4. Therefore, I4 equals 5 amperes. Note, when calculating a current, if the value turns out negative, this simply means the current is flowing in the opposite direction. The following example is in the accompanying workbook, Resistive Circuits, Kirchhoff's Current Law. Find the value of the current I. It does not matter if we can see the entire detail of a resistive network, provided we have assurance that the currents shown represent all the currents entering or leaving the network, then Kirchhoff's current law still applies. So, by KCL, currents in equal currents out. Substituting values, 2 plus 6 plus 4 equals 5 plus I plus 1. Simplifying, 12 equals 6 plus I. Rearranging, 12 minus 6 equals I. Therefore, I equals 6 amperes. Kirchhoff's voltage law, KVL, states that around a closed loop, the sum of the voltage sources or potential differences acting in a clockwise direction equals the sum of those acting in the anti-clockwise direction. Or, more simply stated, around a closed loop, clockwise voltages equal anti-clockwise voltages. By inspecting the circuit shown and by making the assumption E1 is greater than E2, we can set the current direction and draw on the rest of the potential arrows. The clockwise and the anti-clockwise acting voltages may then be identified. By KVL, clockwise voltages equal anti-clockwise voltages. V1 plus V2 plus V3 plus E2 equal E1. The following example is in the accompanying workbook, Resistive Circuits, Kirchhoff's voltage law. Here we have been given a circuit with potential arrows and the current direction shown. The question requires that we should determine the value of the voltage V3. By KVL, clockwise voltages equal anti-clockwise voltages. So, V1 plus V2 plus V3 plus E2 equals E1. Substituting values, 3 plus 5 plus V3 plus 2 equals 15. Simplifying, V3 plus 10 equals 15. Rearranging, V3 equals 15 minus 10. Therefore, V3 equals 5 volts. Note, when calculating a voltage, if the value turns out negative, this simply means the calculated voltage is acting in the opposite direction. The following example is in the accompanying workbook, Resistive Circuits, Kirchhoff's voltage law. In this example, we are required to find two voltages, VBD and VBC. The suffix letters indicate the direction of the potential arrows, and in both cases, the potential arrows point to the B terminal. It should be noted that in this example, we have more than one closed circuit. There is loop ABD, loop BCD, and finally, loop ABCD. In order for a loop to be useful, it should contain one and only one unknown. So, for the first voltage, VBD, the loop ABD meets all the requirements. Taking loop ABD, by KVL, clockwise voltages equals anti-clockwise voltages. Substituting the values, 15 equals 3 plus VBD. Rearranging, 15 minus 3 equals VBD. Therefore, VBD equals 12 volts. Now that we have a value for VBD, we can use loop BCD to find VBC. Taking loop BCD, by KVL, clockwise voltages equal anti-clockwise voltages. So VBD plus 8 equals VBC. Substituting value for VBD, 12 plus 8 equals VBC. Therefore, VBC equals 20 volts. Finally, now that we have found both values, we can use the loop ABCD to check our answers. If the numbers are correct, then the equation clockwise and anti-clockwise should balance. Taking loop ABCD, by KVL, clockwise voltages equal anti-clockwise voltages. Substituting values for VBC, 15 plus 8 equals 3 plus 20, which both equal 23. Kirchhoff's voltage law, KVL, as the name suggests, only deals with voltages. So the diagram should show all the potential arrows and, where necessary, use Ohm's law to convert all other values to voltages. So applying KVL generally to the diagram shown, for loop ABD, clockwise voltages equal anti-clockwise voltages. So E1 equals VAB plus VBD. Applying Ohm's law, E1 equals I1 times R1 plus I3 times R3. For loop BCD, clockwise voltages equal anti-clockwise voltages. So E2 plus VBD equals VCB. Applying Ohm's law, E2 plus I3 times R3 equals I2 times R2. Finally, loop ABCD. Clockwise voltages equal anti-clockwise voltages. So E1 plus E2 equals VAB plus VBC. Applying Ohm's law, E1 plus E2 equals I1 times R1 plus I2 times R2.